Hey, Dr. Clark here, and in this preview video, we're going to be looking at section 7.1 on the Laplace transform. Let's take a look. So first, you might wonder, what is a transform? And you can think of it sort of as a machine. It's really a mathematical function in a way. But normally, when you think of a function, you're going to, like the function x squared, you put in the number 2, you get the number 4 popping out, right? You put in a number, you get out a number. Okay, but a transform is different. You're going to put in a function and you're going to get out a new function, right? So one example would be like differentiation, actually. So if you put in the function x squared, a different function 2x comes out. So it transforms one function into another function. That's one way to kind of think about what we're doing. That's not exactly what we're going to be doing here, but that's one way of thinking, what kind of mathematical thing would take in a function and spit out a new function? Well, that's one way to kind of think about it. All right, so it's going to have some input function and then some other functions going to be output. And we're going to do this because the output function is going to carry over properties of the input function that we're interested in the same way that differentiation carries over properties about the slope of the input function, right? It's sort of this notion of transform is all about how one thing gives you properties about the other thing, okay? And why is this useful? Well, one example is the so-called Fourier Transform. And what you might have there is, for example, look at this blue function here. This blue function is a combination of two different sine functions added together, okay? And so if you think about blue being, this blue here is really the sum of these two blue functions. But you didn't know, you just had the original function and you didn't know which two sine functions were added together to give you this function here. Well, what the Fourier transform would do is it would run the original blue function through and it would spit out this little frequency chart with these two spikes. And the spikes would correspond to the frequencies of the component functions that are building up the original function. And so Fourier transform rather is really important for picking out particular frequencies in a given signal. Here's another graphic of the same thing, a more complicated. The input function here is some, it looks like it's made up of a bunch of sine functions, but which ones? It turns out to be these three ones, and if you took this and ran it through the Fourier transform, the output would look like this, and you would see these spikes here, and the spikes would correspond to the frequencies of the component sine functions that are turning into the given sine function, okay? So Fourier transform, which isn't really going to be our focus in this class, but is really important, is a transform where you take in some input function and it spits out frequencies that then tell you what the component functions are, okay? Well, in differential equations, it's going to be similar. We're going to sort of throw in a differential equation and we're going to be expecting that e to the t is going to be the answer, but which e to the t, right? Is it e to the 1t or e to the 5t or e to the 10t? Well, it's kind of going to be like the spikes are going to correspond to the frequencies of e to the t that are going to solve that differential equation, okay? And so Fourier transform is really important for decoding, signals. And I think there's a lot of applications in this with sound engineering. If I'm recording this video and there's some like hum or some whine of some, machine in the background and I want to pull that signal out, well, I could use the Fourier transform to basically run the signal into frequency domain. I could delete that spike frequency and then run it back into time domain. And the new signal I would get would be basically the original signal minus that high frequency whine that was in the background. A few years ago when the World Cup was in South Africa, all the people in the crowd were whipping around these vuvuzelas, and it had a particular frequency hum. And what they would do then with the live video broadcast, would they be running Fourier transform in between the 10 seconds between when they videoed it and when it went quote unquote live, they would delete out that high frequency hum so that the crowd or you watching on TV wouldn't hear just wow, 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 wow the whole time and wouldn't hear anything else. So this is really important. We're going to be taking this important idea and we're going to be using it to solve differential equations. Okay, that's what this class is about. But it's part of a broader ideal. And what this is going to actually look like for us is this kind of giant messy equation here. But let's take a look at it here. T, I'm just standing for transform. Y is an input function. So we're going to think of Y as like the signal. And we're going to transform that signal. And the output's going to be a new signal, capital Y. Okay? And in this case, I'm using the complex number z because this is the most general way to write the transform. But what happens is if you put z as just a real number instead of a complex number, if you just put in what we usually put in s for the real number version of z, you'll get the Laplace transform. If, on the other hand, you put in like is and no real part, so just the imaginary part for z, so if you put in like is right here, then you'll get the Fourier transform, okay? And so remember, e to the it is cosines and sines. So if you're looking for sines and cosines, you put in that e to the that is, right? So it's e to the it, which is really sines and cosines. If you're looking for e to the t's, which is what we're looking for when we're solving differential equations, then you put in just the real number s. Okay, so both Laplace and Fourier actually have this general description. And we're going to focus on Laplace in Chapter 7. Okay, so that's kind of an introduction to the whole chapter, but also this section. In this section, we're going to sort of learn from that definition, how do you compute the Laplace transform. In later sections, we'll actually use it as a tool to solve differential equations. So there's your introduction to Chapter 7, and we'll see you in class.